I got everything. All right. I will begin with a word of prayer. I will try to begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for the students. Just ask you to guide our steps today. Help us to glorify what we do and understand a little bit more about circuits together, Lord. In your name I pray, Lord Jesus. Amen. So let us talk more about the circuit problem. I was going to talk about the energy stored in capacitor today, but I forgot to prepare for that, and I don't want to wing it because bad things will happen. So I'm going to come back to that. My apologies. I need to explain the Q squared over QC formula to you, and also talk about the larger problem of how much energy is stored in an electric field. There's something interesting to say there. But let me say less interesting things today. Let's just look at how to solve circuits. I'm sorry, that's not, what am I talking about? That's the most interesting thing, right? So let's get started. Example 1. I'll start out real easy. Suppose we have a voltage source here, let's say V0, right? And then over here you've got a resistor, and then you've got another resistor like so, all right? R1, R2, right? And just for the sake of specificity, let's suppose that this one is 10 kiloohms, and let's let this one be 20 kiloohms, right? So we'll call this point right here A, and I'm going to say that this right here is where we've got, you know, the ground zero down here. So my question is, what's the voltage at A given V0 equals to, let's say 30 volts. All right, so there's the problem. We want to find the voltage at A, and we'd also want to find the current through the circuit. So what should we do? We go, okay, well, we've got 30, so we find the equivalent resistance is R1 plus R2, right? So the equivalent resistance here is just 30 kiloohms. And so my current times the equivalent resistance should be equal to my voltage. So that tells me that the current is the voltage divided by the equivalent resistance, which in this case, 30 volts divided by 30 kiloohms, which gives me 1 milliamp. So there you go. There's the answer to one of my questions. We have 1 milliamp of current flowing in this circuit. So let me put some plus minuses in. So minus plus. So if the current is flowing this way, we're lowering plus to minus like that, right? So what's the voltage at A? 10? Well, the voltage at A, there's two ways we could look at it. The one way we could look at it is V0 minus I times R1, which would be 30 volts, minus 1 milliamp times 10 kiloohms, which is otherwise known as 10 volts. So that would be 20 volts. The other way we could look at it is VA is equal to 0 plus IR2. See, because the other way to look at how to get to A is you start from here, which is by definition 0 volts, and we go minus to plus. That's an increase in voltage since the current's flowing that way. And we just found that the current's positive, so it really is flowing that way. And so I get, 1 milliamp times 20 kiloohm, which, lo and behold, is 20 volts. So any way you slice it, the voltage at A is 20 volts. So 10 volts is the voltage dropped from the top. of the circuit to get down to the 20 volts a day. Any questions so far? Let me try another one. Let's see here. What if we had, I'll make it 100 volts. And over here, I had, I don't know, 60 ohms there. I've got, let us say, I don't know, 100 ohms. And this will be, I don't know, what do you guys want? 40? All right, I'll take it. Interesting choice. Like that. And let's throw in another battery down here. Like that. Let's make it 42 volts. I don't know what that's going to do, but we'll figure it out. So how should we figure this out? Adam. Let's see here. Well, this one goes minus to plus, and this one also goes minus to plus, but let's think about that some more. If this is the current I, then I goes down here, right? Plus minus. And then that current is I'm going to call that I1, right? And then that current splits in two, right? Not symmetrically, but let's suppose that we got I2 goes that way and I3 goes that way, right? If that's the situation, can you tell me how I1 and I2 and I3 relate? What's the relation here? Very good. I'll allow it. Then, well, let's see here. So we got plus minus, plus minus. Now the deal is, I told you guys, we add up the voltages around in a loop, right? So, so I guess the question, we should stop for a second and ask ourselves to figure out some questions, right? Like, let's figure out, first of all, let's call this point A, let's call this point B, right? So here's some questions we'd like to answer. We'd like to find I1, I2, I3, VA, and also VB. And we're gonna define the ground to be right here. So that'll be 0 volts right there, all right? That's the problem that's given. So actually, can you tell me what VB would be then? We can figure that out without any further work. What's VB equal to? 42 volts would be correct because it's 0 here and we're going up 42 volts. So 42 volts would be correct. So there, we got that one done. Yay. Now, so yeah, there is a shortcut to doing this problem in terms of lumping the two batteries into one battery. You could do that, right? But I'm not going to do that. I'm going to think through it. And the way to think through it, of course, is to make a loop. The sum of the voltages is 0, right? So I've got 100 volts, all right, minus I1 times 60 ohms, all right? And the loop I'm going to make, it's going to go this way. So you could go either way. I'm going to go the 40 ohm way, though. So minus I2 times 40 ohms, all right? And notice what happens here. I need you to see this. So as we go around this loop like this, right? Notice that there's an asymmetry in the way the batteries appear. I go minus to plus on the 100, but I go plus to minus on the 42. Which is why if I put a plus on the 100, there must be a minus on the 42. Because they're oppositely situated as we're adding the voltages around the loop. Now it doesn't really matter if you go clockwise or counterclockwise. You just got to make a choice and stick to it, right? I could have gone the other way and I could have put the plus on the 42 and the minus on the 100, but I have to be consistent in my conventions. So anyway, now we're back where we started, so that's equal to 0. And so what you see is, what we really have is 100 minus 42, which is 58 volts, is equal to, 60 ohms times I1 plus 40 ohms times I2, right? We have that. We have I1 is equal to I2 plus I3. What else do we have? Can you guys tell me anything else? It's kind of, what part of the circuit have we not, this is 1. This is equation 2. There's a third equation to see here, which is what? What have we, yeah. We forgot the 100. I didn't forget it. I just haven't used it yet. So the other thing we could do is go, oh man. My apologies. Maybe I'll be better Wednesday. Who knows? Weirder stuff has happened. So if you look at it, you can do a loop right there, right? And if you look at that little loop right there, I've got 40 ohms times I2 minus 100 ohms times I3. Or honestly, and that's equal to 0. So of course, that's probably not how I would write it as a student, and you don't have to write it that way if you don't like it. Perhaps you find it more natural. I probably find it more natural to simply say that 40 times I2 has to be equal to 100 times I3, right? Because basically, the voltage on the two resistors has to match, right? So Ohm's law for each gives me the voltages should be equal. So I could just say 40 I2 is equal to 100 I3. So now let's look at this. We got 3 equations, we got 3 unknowns. How should we solve these things? What do you guys think? With a matrix would be, that's a good answer. Can we get away with not doing matrix stuff here? That's got 1, 2, 3. This one's got 1 and 2. This one's got 2 and 3. I guess if we substitute 3 into 1, what does that give us? We get I1 let me solve this for I3. So that's what? For a 2I2 over 5? I don't know. Whatever, I'm just going to leave it as 4. I like 10s. I'm going to keep the 10. 4I2 over 10, right? Did I do the math right? I hope. I don't trust myself. I think it's okay. All right. So I1 is equal to I2 plus I3, which is 4I2 over 10. So of course you've got 1.4 I2 here is I1. Then, let me call this thing 4. Plug 4 into the other equation, which we haven't used, which was 2. And that gives us what? It gives us 58 volts is equal to 60 ohms times, too close to it, I1, but that was 1.4 times I2, plus 40 ohms times I2. Now, one of you said use a matrix. That's actually really good advice, but it possibly won't help you on the test unless you have a matrix calculator. Do you have a matrix calculator? Yes. Well, that's good, I guess, if you know how to use it. So here we have 124 ohms times I2. Apparently I2 should be equal to 58 volts divided by 124 ohms, which is about 0.4677 amps, or if you like, 467.7 milliamps. All right, so there's my I2. And then once you know that, what's I3 equal to? It's 0.4 times I2, right? What's that? I3 is 0.4 I2. So I get 0.187 amps. There you go. Or if you like, 187 milliamps. And what's my I1 equal to? I2 plus I3, right? So I got to add those guys together. I get 0.655 amps for that one. Now my question is, does this all make sense? Like, let's work it out, you know? So is 100, what's 100 times I3? What do we get? 140. I think we should get 18.7 volts here. That's what I got for 100 times 0.187. Is that the wrong thing to multiply? I3 was 0.187, yeah. I2 times 40, what's that? 0.4677 times 40, I get 18.7. Yeah, so 18.7 volts, however you slice it, either through the 100 or through the 40. Either way, Ohm's law gives me 18.7 volts across the parallel combination. And then I also have the 60 ohm, my I1 goes through that, right? So 0.655 times 60, I've got, so this guy right here gets a 39.3 volt drop. So I've got 39.3 volts here. I've got 18.7 volts there. And if I add those, which is appropriate given the signs of everything here, I get 58 volts. Does that make sense? It does make sense because what you guys were proposing at the start was not crazy. You could trade this for the circuit that's got a 100 minus 42 volt battery and an equivalent resistance of what? Well, whatever that is. I don't know what the equivalent resistance is, but you could trade it for this with, these three resistors. Of course, at that point you could use the equivalent resistance idea. You guys have a question? And of course, that would have been a shortcut that might have probably make it faster, right? You could look at this way. But can we always make this kind of shortcut? No, it's not always possible to do that. Let's look at one where it's not possible to make such a shortcut. So sorry I haven't posted the recommended homework from the end of the chapter yet. I do mean to. I've just been kind of sick and I keep forgetting to do it. All right. Oh, I meant to send the attendance sheet around here, lest I forget. Here you go. Yeah? I'm sorry, what? Word problem.
How do we know that like the bathrooms are opposite?
The symbols,
Wait, will we have a diagram?
usually. I mean, I almost never give these in words because of those ambiguities. Yeah. Now, if I'm smart, I'll write the problem. I'll say, like, if this circuit's possible, find the current and the voltage. Every so often I write a circuit which is impossible, so you gotta watch out for that. But yeah.
So, for example, too, how would we do that one if there wasn't the 60 ohm resistor?
If there wasn't,
Like, how would we see that?
oh, if the 60 ohm wasn't there, you just have, you'd have I2 and I3. I don't know what you mean. Just a second, let me try. I'll redirect it over. So you're saying you got my 100 volts here, right? And I'm going to write it this way instead. I got my, what was it, 42 volts over here, like that. You're saying take the 60 ohm out of commission. So that just leaves us with this parallel combination here, right?
So would you just do the equivalent resistance?
We've got 100 and, yeah, you could just, I mean, I think you could do that. What was I? I can't remember anything more than 3 seconds, 40 ohms. So, yeah, the way I'd solve this would just be to go, okay, well, now that we've learned our lesson, we could think about that as a 58 volt, you know, and this would be, you know, 4 times 10 over 140 ohm equivalent resistance. 4 times 100. Oh, yeah, that's probably a good idea. Thank you. Whatever that is. Does that answer your question? And then you can go from there and find out the current in that, and yeah.
So you would do the method you wrote on the bottom, not the one we used.
Well, you can always use the loops and the Kirchhoff's current laws and voltage laws. These are general. It's only sometimes can we do the equivalent resistance thing. Let me show you an example where we can't. So this example, we're forced to do the algebra, all right? So like, let's look at this one. So suppose we've got a 20 volt source here. I've got a resistance R1 here. I'll call this point A. I've got a resistance R2 here. All right. And then and then over here, oops, my bad. That was supposed to be another voltage source. I've got a 30 volt voltage source over there. All right. R1. All right, yep, that's it. We're going to make, and here's the deal, we're going to make R1 equal to 2 kiloohms. And we're going to make R2 equal to 5 kiloohms. All right? Furthermore, I'm going to define. All right, and so when I make a definition, it defines current flowing this way as positive. So this is I1. And then I'm going to define current I2 as going this way. I'm then going to define current I3. It's going to be like, you can't define the current going that way because it's going a different way. Well, if you see that, very good. You have an excellent intuition. However, I can make whatever definitions I want, and I do so choose to do so, and so I do. And if the algebra turns out to be negative, that just means that my picture is not indicative of where the current's actually flowing. I'm getting ahead of the story, but I perceive a disturbance in the force, so I'm just addressing it. All right, so great. Let's find the voltage at A, and let's find, current 1, 2, and 3. And as per my usual laziness, I'll just stick the ground down here because why not? All right. So let's find the currents and the voltage at A. So what are we up against? So first of all, I usually draw in like little plus minuses just to keep track of things, okay? So I go minus plus like this. Current's going this way, so it's a voltage drop like so, voltage drop like so. And there's a voltage source over here. That's all I can say about that. All right? Actually, you really should be able to tell me what the voltage is at A here without further calculation. What is it?
30.
Yeah, so VA equals 2. So this is the setup. So far, this is just a setup, okay, guys? I'll put the solution below that. So I heard VA equals to 30. That's basically just by the definition of voltage source, right? And actually, if we know that, we probably could figure this out easy. So what's I3 equal to? So I3 should be equal to the voltage at A divided by R2, right? Because that's Ohm's law. Because if this is 0 volts, the voltage drop is VA minus 0. I'll write it that way. VA minus 0, which is 30 volts divided by 5 kiloohms. And I think somebody told me 6 milliamps. Cool. 6 milliamps there. That's great. So that was some low-hanging fruit. What's I2?
11.
11, why?
Because KCL.
Because KCL. Well, why do you know I1 is?
Because math.
Because math, okay. Let's work that out. So, I mean, I'm not just asking, I really am asking to make sure I'm not missing something like obvious. Sometimes I just miss something symmetry or something that's easier, and I don't want to overcomplicate it, but I do think math is required here, truthfully. So let's do the Kirchhoff's voltage law around that loop, right? So we've got 20 volts minus I1 R1 minus I3 R2 equals to 0. But you should recognize I3 R2 as the thing we just did, right? Like this is literally 30 volts. That was what we just went through. That's 30 volts. And as such, this tells me that 20 volts minus 30 volts is equal to I1R1, which tells me that I1 is minus 10 volts divided by R1, But R1 was 2 kiloohms, so this is minus 5 milliamps. I1 is minus 5 milliamps. This can happen. All that means is that the current's actually flowing this way, right? And then what? And then, like you said, Kirchhoff's current law, right, at the node, to get the rest of the story here is I1 plus I2 is equal to I3. So that tells me that I2 is I3 minus I1, which is 6 milliamps minus a minus 5 milliamps, also known as you told me a second ago, 11 milliamps. Are we understanding, or my promise that we needed to do algebra was a little bit far-fetched. Let me try to make one worse. I'm going to get a worse example here eventually. Eventually, I'm going to get an example so bad we're going to actually have to do algebra. Let's try it again. So example 4. What happens if we put a voltage V1 here, put a resistance R1 here, put a resistance R2 here, put a resistance R3 here, put another voltage source like so, like that, all right, and V2, and I don't know, just for kicks, throw it at R4 down here, and I'll leave this branch alone. I'll put the ground here again. So let's see if we can, let me define the currents. I guess if I know what's good for me in here, I'll define the currents, because otherwise grading is really, if I let you guys define the currents, oh, so many choices. But I'll be lazy. I'm going to make the current I1 go like so. I'm going to call this guy I3. I'll call this one I2. And that should be enough. See, because you notice how this works? If I3 is going here, since these are elements in series, series elements share the same current. So my I3 up here is the same I3 that goes down here, right? Does that make sense? I hope. So the easy part is I1 plus I3 equals to what? I2, we got that, great. And then I need to write down Kirchhoff's voltage law around the loop, if I can. So what do I got? I've got, oh, I meant to put my plus, I try to put my plus minuses in to keep me honest. Let me do that. Do 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 doodly do minus plus, and I always go based on the current that it's going through here. I1 goes, I2 goes to plus minus. This one goes plus minus like that, minus plus like that, plus minus like that. All right. So following my for the left loop, we've got V1 minus I1R1 minus I2R2 equal to 0. Right loop. So you got to pick a starting point, right? Where do you guys want me to start?
V2.
Start here? All right, let me draw an arrow. Which do you guys want me to go clockwise or counterclockwise? Up to you guys. Counterclockwise? So where am I, what point am I starting at? Right here? I'll start here. You said you guys want me to go counterclockwise. So that's like this, right? So if I do that, I go V2 minus I3 R3 minus I2 R2 minus I3 R4 equal to 0. Well, this is, I really wanted some, these examples are not, there's a certain thing not happening in these examples I wanted to happen. But I just have to be content with it. So, all right, that's it. So let me rewrite this. We've got I1 minus I2 plus I3 equals to 0. We've got I1R1 plus I2R2 equal to V1. And we've got, excuse me, I2 times I2R2 plus I3 times R3 plus R4 is equal to V2. All right, that's, I'm cleaning it up a bit, all right? That's like, I think that's a nice way to look at this system of equations. And so some of you guys are saying, well, I should use matrix techniques. I totally agree with you. So we should really look at this as something like, well, one thing we could do is like divide by, you know, for example, like kilo ohm. So let's for the sake of specificity, let's suppose that R1 is, I don't know, 2 kilo ohms, and R2 is 7 kilo ohms, and R3 is 5 kilo ohms, right? So if and let's let V1 be 10 volts, and we'll let V2 be, what do you guys want? 30 volts, whatever. All right. If we do all that, then the system we're up against, we could look at it this way. We've got 1, minus 1, 1, 0. We've got, so if I divide by a kilo ohm, I'm going to have V1 over a kilo ohm is 10 milliamps. So you can look at that. It's like 10 milliamps here. And V2 over a kilo ohm would be like 30 milliamps. And R1 was, so I got 2. Oh. R4 is equal to, let us say, what do you guys want? I mean, 4 kilo ohms. How about that? There we go. Why not? So 2, R2 was 7. So put a 7 here. Man, 0. Here I have no I1 term, so there's a 0 in the I1 spot. Right? So this is the I1 spot, this is the I2 column, this is the I3 column, and my R2 was 7, And R3 plus R4 is 9. And we could solve this system of 3 equations and 3 unknowns by substitution, like I did at the start of class. We could do that, right? But it's much smarter to use matrix techniques. By the way, even if you don't have a graphing calculator, even if you simply have this Casio 115, yes, this has a matrix simplifying calculator in it. Believe it or not, it's in there. You can find it. And it will do what's called row reduction on this, and it will tell you the answer. It's in there. So if we calculate what's called the reduced row echelon form of this, that's what you want. That's what you want. And so what that should give us is 1 0 0 0 1 0 0 0 1, and then the last column. Now I'm not going to do that by hand because I'm tired. And also, I want to emphasize actually that it is important for these kinds of problems. If you're allowed to use technology, by golly, you ought to be using technology, right? So I'm going to allow myself to use technology for the moment to prove a point, if I can. Doo-doo. Now there's tons of things online to do this with. Like we could use Wolfram Alpha, we could use any number of things, but I'm personally fond of a particular website I like to use when I teach Math 221 here. So I'll show you guys that, and you can take it. Actually, I really don't like that because I want a numerical solution here. Well, I'll use Wolfram. All right, so here we go. So you guys will have to tell me. So if you want Wolfram to solve a system, what you do is you just put the system in like one after the other. So like, you guys will have to read the equations to me. I can't see them from here. What's my top row is what? Blah, blah, blah. All right, so I'm going to use X, Y, and Z for my I1, I2, and I3 just for the sake of, ease. So it's 1, 1, what? Is it 1, 1, 1, or is it 1 minus? 1, negative 1, 1. All right. X minus Y plus Z equal to what?
0.
And then what's the next one? 2x plus 7y equal to what? 10. And what's the next one? 7y plus 9 z equal to what? 30. All right, so apparently the solutions, and so if you have your MATLAB, you can use the reduced row echelon form or appropriate matrix reducer command, and we get negative 10/19 milliamps and 30/19 milliamps. Now obviously we don't want to leave our answer in terms of fractions, right? This is physics, so we need to take another step here, get our handy dandy calculator out and find an actual number. So this tells me that I1 is minus 10 over 19 milliamps, whatever that is. That gives me minus 0.52 milliamps, something like that. 0.53. And I2 is 1.58 milliamps, something like that. And I3 is 2.11. Right? And then if I was to ask the follow-up question of what's the voltage at A, You guys figure it out for me? What's VA equal to? We could do V1, right? Minus I1R1, whatever that is. That should also be equal to V2 minus I3R3 if we did it right. We should be able to get the same number 2 different ways. Let's see what we get. So V1, 10 volts minus, well, which is plus actually, so, oh man, plus 0.53. R1 was 2 kilo ohms. So I think if I didn't make a mistake, I got about 11.03 volts, but there's some ground off error going on here. If I try 30 volts minus I3R3, what do I get? $19.5. Uh-oh, I did something wrong. Oh, hold on a second. All right, so you guys, tell me why I'm wrong. Why is this wrong? So I'm saying VA here is V1 minus that voltage because I'm starting here, right? This is here too, right? So all I'm getting, I've completely ignored R4 is my point, right? So I have to subtract I3 R4 as well. And what's that give me? I hope it gives me 11.03. So if I take my 30 volts and I subtract I3, which was 2.1, times R3 plus R4, which is 9, I get, so this gives me 11.1 volts, but you know, I got some round off error going on here, but there it is. Yep.
Why don't we consider R2?
Why would we? I mean, you could if you wanted to. Another way to get VA. So your point is like you want to say VA is just equal to I2R2? Is that your question or comment? I totally agree with you. We could do that too. So I2R2, right? Because it goes from there to there. Great. So 1.58 times what was R2? 7. We get 11.06. So if you want to, don't take the average. It's just numerical mistakes, you know, round off error. My point is to find the voltage at A. You got many choices. You could start here, go to here. You can start here, go to there, or as usual, I have avoided the most easy option, which is to go from here to here. So very good. Thank you. Muchas gracias. All right. Anyway, see you guys Wednesday.